Assalamu alaikum. In this lecture, I will talk about polyelectronic atoms, the Aufbau principle, the electronic configuration of atoms. First, the polyelectronic atoms. This means that atoms with more than one electron. ذرات اللي هي متعددة الإلكترونات. Polyelectronic atoms leads to hydrogen-like orbitals. وهي الذرات المتعددة الإلكترونات في الأخير تعطينا orbitals شبيهة بذرة الهيدروجين. When electrons are placed in a particular quantum level, they prefer the orbitals in the order of S, P, D, and then F. يعني عند إضافة إلكترونات في مستوى من الطاقة، الإلكترونات طبعا الترتيب الأوربيتالز هذه بيكون حسب طاقتها، ودائما هنا عندي S بنضيف فيه إلكترونات قبل P قبل D وآخر شيء هو F. For a given principal quantum level, the orbitals vary in energy as follows. Energy of NS less than energy of MP, less than energy of ND, less than energy of NF. يعني إذا أخذنا أي principal quantum number N، أي level، أي مستوى من الطاقة، ترتيب الانرجي الطاقة لهاي الأفلاك بيكون NS أقل من MP أقل من ND أقل من NF. وهي عندي مثال هنا. Energy of 4S is less than energy of 4P less than energy of 4D less than energy of 4F. طبعا الانرجي بتقدر تطلعها من N plus L اللي هي على سبيل المثال عندي 4S N plus L هنا N equal 4 L 4S is equal to 0 4. إذا أخذت 4P N plus L إله 4 زائد 1 تساوي 5 وهكذا. In this slide here we have the history of the periodic table, originally constructed to represent the patterns observed in the chemical properties of the elements. يعني بداية تم بناء الجدول الدوري بالاعتماد على الصفات الكيميائية للعناصر. طبعا هذا مش صحيح 100%. بعد هيك مندليف اللي هو عالم روسي is given the most credit for the current version of the periodic table because he emphasized how useful the periodic table could be in predicting the existence and properties of still unknown elements. يعني مساهمة العالم مندليف واللي هي زي ما بنشوف الجدول الدوري حالي، لأنه أعطاك يعني مساهمات بناءة في التوزيع الإلكتروني، في إنه يقدر يفسر خصائص موجودة وخصائص لإليمنت لسه مش موجودة. فهي يعني الفيرجن الجديد أو الكرنت فيرجن للبيريودك تيبل بيعتمد أكثر شيء على المساهمات العالم أو جدول دوري مندليف. The Aufbau principle and the periodic table. As we know, the protons are added one by one to the nucleus to build up the elements. Electrons are similarly added to the hydrogen-like orbitals. زي ما بنعرف إنه البروتون يضاف بروتون إلى نواة الذرة حتى يتكون عندي العناصر. بنفس الطريقة الإلكترونات تضاف إلكترون إلى الأفلاك الشبيهة بذرة الهيدروجين. We have an example here. An oxygen atom has electron arrangement of 2 electrons in one S subshell, 2 electrons in the 2S subshell, and 4 electrons in the 2P subshell, as shown in this configuration: 1s2, 2s2, 2p4. Here we have the Hund's rule اللي هي قاعدة Hund. Hund's rule says the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by Pauli principle in particular set of degenerate orbitals. يعني هاي القاعدة بتنص على إنه الطاقة الأقل طاقة للتوزيع الإلكتروني للذرة لما يكون عندي maximum number of unpaired electrons، أكبر عدد من الإلكترونات المفردة واللي هي مسموحة بمبدأ باولي للاستبعاد. إذا كان في عندي أفلاك إلها نفس الطاقة degenerate orbitals means same energy. Here in the orbital diagram for oxygen we can write the following here: 1s2, 2s2, 2p4. S orbital is one orbital or one room, can accommodate 2 electrons, one up, one down. 2s orbital also it's one orbital or one room, electron up, electron down, paired. Now electrons in 2p, p orbital is 3 orbitals. These 3 orbitals, px, py, pz. So we have 3 rooms. The energy of these 3 are equal. So these orbitals called degenerate orbitals. Now the 4 electrons distributed in 2p as here: 1, 1, 1. Then the 4th one comes here paired with this. Not like this. This is wrong. Why? Because Hund's rule says that we have degenerate orbital, then maximize the spin. Here we have the valence electrons, إلكترونات التكافؤ, which means that the electrons in the outermost principal quantum level of an atom is called the valence electron، اللي هي الإلكترونات اللي موجودة في آخر مستوى من الطاقة من الأفلاك. عندي 1s2, 2s2, 2p6. The outermost level here, level 2. In level 2 we have 2s, 2p. We have 2 electrons in 2s and 6 electrons in 2p. So the total number here is 8. So the valence electron for this configuration is 8. Now the elements in the same group in the periodic table have the same valence electron configuration. يعني الإلكترونات اللي بنفس المجموعة في الجدول الدوري إلها نفس عدد إلكترونات التكافؤ، زي مثلا جروب 1A اللي هي الليثيوم، الصوديوم، بوتاسيوم، الروبيديوم، السيزيوم. هذول المجموعة الأولى كلهم آخر إشي يحتوي على NS1، 1 إلكترون في S orbital. Let's start with the electron configuration. Period 1. Period 1, here we have 2 elements, hydrogen and helium. Hydrogen, atomic number of hydrogen is 1, 1s1. So we have 1 electron in 1s. Helium, we have 1s2. We have 2 electrons in 1s orbital, 1 up, 1 down. Now, period 2, start with lithium. Atomic number of lithium is 3, 1s2, 2s1. So, in orbitals here, S1s orbital has 2 electrons, 2s has 1 electron. Beryllium next, no, atomic number is 4, 1s2, 2s2. Boron, 1s2, 2s2, 2p1. Here, for boron, the valence electron is 3. 2 plus 1 is equal to 3. Okay, continue here. Element carbon. Atomic number of carbon 6, 1s2, 2s2, 2p2. Look here at 2p. We have degenerate orbital, p orbital. We have 2 unpaired electrons. According to Hund's rule, maximize the spin. Nitrogen then, atomic number 7, 1s2, 2s2, 2p3, 3 unpaired electron in 2p orbitals. Oxygen, 1s2, 2s2, 2p4. The fourth electron must pair with the first electron here. Fluorine, 1s2, 2s2, 2p5 electrons. Neon, the second noble gas element, atomic number 10, 1s2, 2s2, 2p6. Now we will start with its period 3 with the sodium. So sodium atomic number 11. Electron number 11 will go to the third level, to the 3s actually orbital. Then the electron configuration of sodium must be 1s2, 2s2, 2p6, 3s1. Or we can write it like noble gas structure of the element before sodium, which is neon, then 3s1. Next element, Mg. Mg 12 atomic number, neon 10, 3s2, 13 aluminium, neon 3s2, 3p1, 14 silicon, neon 3s2, 3p2, 15 phosphorus, neon structure 3s2, 3p3, and so on until you reach the third noble gas element, which is the argon, 18. So argon must have a neon structure, 3s2, 3p6. Atomic number of argon 18. Now 19, this is the end of the period 3. Period 4, we start here with the potassium. Potassium, argon structure for S1. Next element, calcium, 20. Argon for S2. In this slide here, we have the method used to write down the electron configuration. Looks like an arrow. Here are 1, 2, 3, 4, etc. So the filling of electron according to the arrow. The less energy or the lower in energy will fill first, and so on. You see here, like this, then here, like this, like this, like this, and so on. Or you have to memorize this series. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, etc. Or in abbreviation here, we have the atomic number in red, here 2, which means the structure of the first noble gas, helium. Atomic number 10, we have noble gas, neon. Atomic number 18, noble gas, argon. Atomic number 36, noble gas, krypton. 54, xenon. 86, radon. So for example, you have X element atomic number of X element is 55. Look here, 55. You can use the arrow here, or you can memorize this. The element, the noble gas element before 55 is 54, which is the xenon. You can write down xenon structure, then 6s1. Now the valence electron is 1, the valence orbital is 6s. This is from group 1. If you have element Y unknown and the electron configuration of this is 58. Same thing here. You have 54 xenon, then 6s2 here, 56. The 2 electron will go to the 4f, 4f2. Here 54, 56, 58. This is from F block, lanthanide. In this slide here, we continue writing the electron configuration for the elements after calcium. Calcium has atomic number 20, so the next element after calcium is scandium. The atomic number is 21. And here we begin the series of 10 elements from scandium through zinc. This series is called the transition metals, or D block elements, because we are filling a d orbital. So scandium has the configuration argon 4s2 3d1. Next element after scandium, titanium, argon 4s2 3d2. Then after that we have vanadium, atomic number 23, argon 4s2 3d3. After vanadium we have chromium, atomic number is 24. So the expected configuration is argon 4s2 3d4. Here a d orbital has 4 electrons, less than half filled by 1 electron. So the correct configuration for chromium will be moving 1 electron from 4s to 3d to become a half filled. So the observed configuration for chromium will be this one. Argon 4s1 3d5, half filled d orbital, more stable than less than half filled. So this is the correct one. The next 4 elements, manganese through nickel, they have the expected configuration. Manganese 25, argon 4s2 3d5, iron 26, argon 4s2 3d6, cobalt 27, argon 4s2 3d7, nickel argon configuration 4s2 3d8. The next element after nickel is copper. Atomic number for copper is 29. The expected configuration for copper, argon 4s2 3d9. Here d orbital has 9 electrons, less than completely filled by 1 electron. So moving electron from 4s to 3d, and the observed configuration will be argon 4s1 3d10. This is the correct configuration. Again, about d orbital, when it's half filled or completely filled is more stable than less than half filled or completely filled by 1 electron. After copper we have zinc. Atomic number of zinc is 30. Then the electron configuration becomes argon 4s2 3d10, and the zinc, which is the end of the first transition metal series. After zinc we have gallium 31, which is argon, configuration of gallium. Argon 4s2, 3d10, 4p1. Germanium 4p2, arsenic 4p3, selenium 4p4, bromine 4p5. End of this period, period 4, we have krypton 36. So these here, from here to here, is D block elements. Here we call it S block elements with helium, and these are P block element. In this slide here we have the periodic table shown in this figure in terms of which orbital are being filled. We have the following notes here regarding this table. Number 1, the n plus 1 s orbital always fill before nd orbital. Example here, 4s orbital filling before 3d, 5s before 4d, 6s before 5d, and so on. After La element, which is lanthanum, and the atomic number for this element is 57, we have 14 elements called lanthanide series. So after La, we have a series element of 14 elements filling 4F from 4F1 to 4F14. These are called lanthanide series. Number 3, after actinium AC, which has the atomic number 89, we have another series filling 5F orbitals, and these are called actinide series. يعني باللغة العربية بسموها مجموعة العناصر الأرضية النادرة اللي هي اللانثانايد والأكتينايد، واللي فيهم العناصر المشعة، فهي F transition elements بسموها، هنا بسموها D transition elements. الخط الأفقي دورة والخط العمودي مجموعة. Okay. Next, another table shows the valence electron configuration are given in this figure. Also, continue in the notes here. We have the group labels: group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. These indicate the total number of valence electrons for the atoms in this group. Example, group 4A has total number of valence 4. Group 5A, we have a valence electron in the outermost 5, and so on. These groups 1A, 2A, 3A up to 8A are called main group elements or representative elements. Again here, this is a D block, D transition elements. Down here we have F transition elements or F block. P block and S block are called representative elements. The last slide here we have an exercise to write down the electron configuration for sulfur and cadmium. Atomic number for sulfur is 16, cadmium 48. So you have to distribute 16 electrons for sulfur, 48 for cadmium. And sulfur will has the configuration of neon configuration 3s2, 3p4. Valence electron is 6 and the valence orbital is 3s and 3p. For cadmium, the noble gas before cadmium is a krypton 36, 5s2 4d10. So this is the electron configuration for cadmium. I will leave this homework for you, but I will explain how to write electron configuration for cations and anions. For example, if you have Na plus, Na atomic number of Na is 11. So here plus means that lose one electron. You have to distribute electrons. 1s2, 2s2, 2p6, or neon configuration for Na plus. If you need to write electron configuration for O or -2. Oxygen, atomic number of oxygen is 8, so you have to add now 2 electrons for this anion. 1s2, 2s2, 2p6. Because here negative charge for this anion means gain 2 electrons or neon configuration. If you have, last example here, if you have scandium plus 2, scandium 21, argon 3d1, because here plus 2 means that lose 2 electrons from 4s, and this is the electron configuration for scandium 2+. Thank you. Bye.